So in the last session, we were talking about vectorization, and the last thing I need to talk about in this vectorization section is I'm going to just briefly talk about OpenMP. OpenMP is a very popular industry standard for doing parallel computing. It has like a lot of different functionality stuff for concurrency, parallelism, but part of what it provides is some functionality for vectorization. So I'm not going to present any of the other functionality. OpenMP has like a lot of great stuff in it. I'm only going to focus on just the stuff that's relevant to vectorization, since that's what we're talking about here. OpenMP 4.0, I think the most recent one, I think it's up to 5.0 now. But anyway, a while back, they added support for like SIMD, in other words, the kind of vectorization that we're talking about in the course. And the way that this is provided, there's essentially support from the compiler. It requires compiler support because you actually put special directives into your code, and then the compiler has to handle them specially. But the directives that you're adding are different kind of things from the things that we've talked about. In particular, the type of mechanism that's used is pragmas. There's a number sign pragma directive that you can put into your code. And essentially, this allows a kind of a very general way to allow for compiler-specific extensions or other extensions to be added to the language. And the basic idea is if a compiler doesn't support that particular thing, it just ignores the pragmas. So for OpenMP, there's basically two types of pragmas that relate to vectorization that we're going to talk about. There's one called SIMD. And this pragma essentially allows us to control vectorization of loops. And then there's another directive called declare SIMD, which allows us to generate vector versions of functions. So essentially functions that we can call from vectorized loops, where the functions themselves are going to be vectorized. And OpenMP, by the way, supports a number of different languages. Obviously, one that's relevant to us in this course is C++, but it supports C and Fortran and possibly other languages as well. And yes, people still use Fortran. There's a massive amount of numerical code that's written in Fortran, and a lot of vectorization. Vectorization often is very important in numerical algorithms, hence the reason for wanting to support Fortran. So in terms of the SIMD pragma, so all of the pragmas for OpenMP start out with OMP, which just stands for OpenMP. And then there's kind of a sub-directives within OpenMP directives. So the first one we're going to talk about is the SIMD directive. So the syntax looks something like this. So you have number sign pragma, OMP, and then SIMD, and then you have optional clauses which you can add on to give kind of additional information to the compiler that's implementing this OpenMP stuff to exert a little bit more control over how, for example, the vectorization is done. And this has to precede a for loop, essentially a for statement. It doesn't work with other types of loops. It has to be a for loop in particular. And the for loop has to be in what's called canonical form, which is just kind of a fancy way of saying it has to be a relatively simple loop, where canonical has sort of a precise definition. But basically, the essence of what it's trying to say is the loop needs to be pretty simple so that the compiler can analyze it and have a hope of doing the things that you want it to do for OpenMP. There's a bunch of clauses that we can stick on the end here, and I'll talk kind of very briefly about a few of them. There's these extra like keywords and stuff you can stick on the end here to control things like, for example, what's the vectorization factor you use when vectorizing and things like this. In terms of what's meant by canonical form for a loop, this is not an exhaustive list, but this is just meant to give you an indication of like some of the constraints that are placed on the for loop. So you can't stick this pragma in front of any for loop. It has to be in what's called canonical form. And so some of the requirements of this is the induction variable, in other words, the looping variable that you're using. It has to be an integer, a pointer, or a random access iterator type. And the reason for this is in order to make it possible for the compiler to have a hope of being able to analyze your code and do the vectorization in the way you want. Because again, if code gets too complicated, it can be very, very quickly reach the point that where maybe the compiler can't handle things. So this makes things much easier for the compiler to analyze. You're quite limited in terms of what you can do with the induction variable. You can like test it like against a value, like compare it to maybe some other value. You can increment it and decrement it, and that's more or less it. Also, the iteration count for the for loop has to be known before you execute the loop. So this means that the number of times you're iterating through the loop, kind of an implication of this is it can't change effectively, like your decision of how many iterations can't change as a consequence of what's happening when the loop is iterating. In other words, you know upfront what the number of iterations are, and there's nothing that could cause you to terminate the loop early, for example. With OpenMP, you can target both inner and outer loops for vectorization. The loop itself has to be suitable for vectorization, so you have to kind of make sure that there's no data dependence problems that are going to cause the loop not to do what you want. And just as an example of code that's actually using this pragma down below here, I have a pragma OMP SIMD, so this is saying I have a for loop that I want to vectorize. And this particular loop here, it doesn't have any data dependencies, because like all the iterations are independent from one another. And assuming that there's no aliasing, which is sort of what's implied here, we're effectively telling the compiler that they're telling the compiler that's implementing OpenMP that there's no data dependence problem, so it doesn't need to worry about aliasing and so on. And it just goes and vectorizes the loop. There's other clauses that we could add on here if we wanted to exert more control. We could maybe say how many, like what vector length do we want to use. If we don't specify, presumably there's some default that it uses and so on. The other pragma is the declare SIMD pragma. So the purpose of this is for specifying like vectorized versions of functions. So the idea is you have some kind of function declaration and you want to, or definition, and you want to force the code for that function to be generated in a vectorized form. So that, for example, you can call it within a vectorized loop that's being vectorized by OpenMP. Because we mentioned before, one thing that can cause problems with respect to vectorization, if you're trying to call functions within a loop, it's problematic because normally, like C++ does not have a notion of like a vectorized function, whereas OpenMP gives you this sort of notion using this pragma. So basically, the declare SIMD pragma precedes the function declaration, and you can also specify some optional clauses that exert finer control over how the vectorization is performed. In terms of a code example, here we have a function called foo. It takes 3 floats, A, B, and C, and then it computes some kind of multiplication and addition involving these values, and then it returns a float. And the basic idea here is suppose that you want to call this particular function from within a vectorized loop that's being vectorized by OpenMP. In order to do this, you kind of need for this to be a vectorized function. So when we put this directive in front of the function, effectively what it's going to do is this A is not just going to be a scalar anymore. It's actually going to be a vector. Like A will be a vector of floats, B will be a vector of floats, C will be a vector of floats. When you're adding and multiplying here, you're going to be doing vector operations. And then the thing that gets returned effectively is a vector of floats as well. Like not vector in the std vector sense, but vector in kind of the vectorization sense. So this is what the declare SIMD pragma does. So as I mentioned before, the SIMD related pragmas can have optional clauses attached to them. And I just want to discuss very briefly a few of the clauses that can be used. I'm not going to discuss all the ones that are shown on this slide and the next one, but just focusing on some of the more interesting ones and also some of the ones that appear in some of the code examples that we'll be looking at subsequently. So the first clause I want to look at is the safe-len clause. And what this does is specifies the maximum number of iterations that can be run concurrently in a safe manner. In other words, without causing problems with respect to data dependencies. Another interesting clause is a SIMD-len clause, which specifies the preferred length of the vector registers to be used for vectorization. Another interesting clause is the align clause, which allows us to specify the alignment of variables in our code. And this can be exploited to get better vectorized code by the compiler. And 2 other clauses are the in-branch and not in-branch clauses. These are used in conjunction with trying to produce vectorized functions. And the in-branch clause specifies that the function that's associated with this clause will always be called from inside a conditional statement in the body of a vectorized loop that's been vectorized with OpenMP. And not in branch means that the function will never be called from inside a conditional statement. And this slide continues the list of clauses for the SIMD related pragmas. On this particular slide, however, there's not any clauses that I really like to discuss. These 2 slides go into a little bit more detail than what we need to know for the purposes of this course. So I'm just going to skip over the clauses that are listed on this slide. And then just to give an example of actually vectorizing a loop using OpenMP, we have this multiplication function. So we're taking in 2 one-dimensional arrays, A and B, and then we're going to essentially multiply them, take the product of the corresponding elements from the 2 arrays and then write them into this other array C. And we want to vectorize this loop here. So we're going to do this rather than going through all of the stuff that we did before. We're using like restrict and assume align and stuff like those functions. Instead, we're going to use this with do this with OpenMP. So we use this pragma statement, OMP SIMD, and here we're using one of the clauses. The reason for this is we want to say something about the alignment of the data that's being used in the loop. And we know because of the way this function is being called, like this is just the way it's defined, and the person who designed the code, they're saying that the user has to pass in as a template parameter here the alignment for A, B, and C. So because this is being provided, the code can exploit this. So this is basically being passed through to OpenMP, and we're saying that A, B, and C are all aligned with the alignment align. So it's going to do the vectorization based on the assumption that the data has that particular alignment or better. And it really is just kind of that easy. I guess kind of baked into this is the fact that there's no data dependencies, which implies, I guess, there's no aliasing, because if there was aliasing, this would introduce data dependencies into the loop. And then if we look at the code down below that's actually using this multiply function, so here is where it's being invoked here, and we're passing in like the three arrays A, B, and C, which are these arrays here. And we were careful to make sure when we define these arrays that they're all aligned with a particular alignment. The alignment that we're passing in here with a line is given by this constant expression up above. A line is equal to 16 times a line of float. So in other words, the alignment that we're using is going to be 16 times more strict than that for an object of type float. And so we've aligned all of these arrays with that alignment. And then when we call this multiply function, we're passing as a template parameter this align value. So this is making sure that the alignment that we're promising in here, that these arrays A, B, and C have, actually is satisfied by the code. And you can see also the way that we're invoking a multiply here. There's no aliasing that can happen because A, B, and C are all distinct arrays. There's no way that they can overlap in memory because they're actually distinct arrays. So there's not any data dependencies and so on. So everything should work okay, assuming that the OpenMP implementation doesn't have any bugs in it. Which shouldn't be the case as long as you have a stable compiler. Any questions?
Is there any risk if you omit that GNU and no inline?
Oh, sorry, yeah, I didn't think to comment about it. The only reason I put this in was I don't have it on the slides here. Maybe I should add it in a future version, but I was looking at the assembly code that was being generated because I was just curious, like, how did it compare to when we were doing things the other way? I don't remember offhand how it looked, but the thing was it made it more difficult, or it was just more awkward when I was looking at the code if it inlined the function, because then it kind of got mixed up, and also the optimization maybe merged part of the code in with the main function. So all this is, this is what's called an attribute. In C++, there's things that you can put into pairs of double square brackets, which can cause different sorts of behavior. Like normally, the compiler maybe just ignores it if it doesn't know what the attribute means, but GCC and I think Clang as well support this attribute, which says don't inline the function. Because for a function like this, there's a good chance the compiler, if optimization is turned on, that it will actually inline this because the function is quite small. And I just didn't want it for the purposes of what I was doing for it to be inlined. But it will work fine if it's inlined. It's just that I was looking at the assembly output and it was more convenient if it didn't inline it for this purpose. Any questions? Or any other questions, I should say? Okay, and then the last code example I have is just an example of using the like a vectorized function. So in this case, what we have is a vectorized loop down in main here, where we're trying to call this function func, and we have basically we're doing stuff with arrays here, array A, B, and C. And the idea is we want to call this function in a vectorized kind of manner. And like normally this sort of thing can't really be done because C++ doesn't really have a notion of like a vectorized function. But with OpenMP support in the compiler, you can actually do this. So what happens is we declare a vectorized version of this function. So up above here where the declaration of func is given, you'll notice that it's preceded by this pragma. And this pragma here, this declare SIMD pragma, is saying I want to, what immediately follows it must be a function. And what it's saying is I want this function to be a vectorized version of the function. And I'm using one of these clauses here just to say that when this is basically saying whenever this function is called, I promise that it will never be, it's never going to be called like inside a conditional statement inside the loop that's calling it. And you can see here that this is not inside of like a conditional. There's no like if wrapping this function call. So this, we're just kind of saying, making the promise that this won't happen. And presumably this is because there's some optimizations that can be done by the compiler knowing this. So essentially what's going to happen here, like when the compiler vectorizes the loop here, what's going to actually be passed into the function is going to be like a whole bunch of A values, like a vector of A values over some range of indices and a vector of B values. And the value that's returned is going to be a vector of values, which then get assigned to like a vector of C values. So essentially the A here is really going to be a vector, but again, not like a std vector, but just like a vectorization kind of vector. And B also will be a vector. Then these adds and multiplies are going to be vector operations. The thing you're returning will actually be a vector. And so even though the type is float, the reality is it's going to be like a vector of floats that get returned back. So this is just a very simple example of using OpenMP to have a vectorized version of a function. Any questions? So that brings us to the end of the unit on vectorization, and that also brings us to the end of the course. So we're finished early today.